One more presentation and we'll hand things over to Roger here. And Roger, tell us about another new feature inside Mathematica 9, random processes.
All right, thank you. So I'll give you an introduction or an overview to random processes in Mathematica 9. So random processes is the major new feature for probability and statistics. You've already seen a few. This is one that we spent a lot of effort on. Some of the big classes of processes that we will eventually talk about include Markov processes, queuing processes. We've all been in queues, time series, which many of you probably are familiar with, stochastic differential equations. All of these have sort of a wide variety of things, and these are some of the examples that you can find on the marketing pages, and there's many additional applications in the documentation. We'll cover some of these, but most of it you will find on those pages. So the first part of this talk, I'm going to try to give you a little bit of a framework, a way to think about this, and then we're going to dig into these other classes of processes. So first of all, a random process is the analog of a dynamic system when you think of deterministic things. So things like differential equations, difference equations, and so on, these are things that we've had in Mathematica for a long time. Now, if we allow randomness to also sneak into the system, then you don't just have one path, you have many possible paths that the system can generate. So one aspect of that is that we can have things that have various classifications like this, that the time, either there's sort of a discrete set of times like the integers, like a sequence, or continuous time, that for any time that the process has a value, but also the actual value can be both continuous and discrete. So let's go and look at that, a few examples. So those of you who are familiar with distributions will recognize the framework that we've set up. So each process, it has a name that ends in process. The few simple processes just have a few parameters. If I want to simulate a process, I need to indicate over how long, what amount of time. If I do that, I'll get something back that's called temporal data. This is something that's independently useful for dealing with time series data, such as you might get from all kinds of places. Now let's just look at the plot of that, and here we can see what that process actually looks like. So Poisson process is a sort of a simple process. It kind of models traffic flow, for instance. So this one will count from 0, and then it will just sort of add an integer increment every time some event happens. Every time a car passes, it will count up. So this one has discrete state, but it has continuous time. At every point in time, you have an actual count. Now, you can also generate many of these simulations. So even if you generate many of them, it will store it in temporal data. And if we plot those, you can see that we have many possible sort of traffic scenarios. So here is, standing out by the road 10 different times counting cars, if you like. And this is how your count would have varied by time. Now, just as for distributions, we can generate data. So this one will generate data. It will allow you to sort of simulate something that goes on and see how it's going to behave. We can also use data that we use from measurements and so on and figure out which model is the best of all possible models in a class to describe that data. So let me generate some synthetic artificial data here by simulating. And now I can take that data as input, and I can indicate which family of random processes do I want to consider. So here I say I want to consider the Poisson processes, but I keep the parameter as a symbolic thing, and it will find the best of all possible parameters that fit that. In this case, it's a maximum likelihood fit. This is not very good because I don't have that much data. If I extended the data either longer in time or more copies, I would get more data. So let's do the 10 times counting cars, and now when I fit it, you can see it's getting closer. And the more data you get, the closer, the better your approximation or your estimation will be. That's kind of a big topic in itself, but we've made it just as simple as estimation for distributions. Now, here's an overview of all the processes that we provide with Mathematica 9, and there's about 30 of them. This group here with continuous state, these are often known as time series processes. Well, that's what they're known as. These guys here are stochastic differential equation type processes, and we played with just one, which is a Poisson process. And all these discrete state ones, they're typically finite state or infinite state kinds of processes. Another concept that's useful to understand as the backdrop, and all the things I mentioned now, they apply to all processes, regardless of which one. So these are universal kinds of things. Now, if I look at the process at a certain time t, and so we see here along this axis I have time t, and along here I have the state value. If I look at any one of those slices, and let's do it, instead of looking at that, I'm going to go back to that graph, but let's say that I run some simulations that you saw me do. I can put I can slice my data, I can put a cut in my data and see here the red dots are all the places where my path crosses that line. If I use those as data points and I estimate a density function from that, like the smooth histogram function in Mathematica, then the bubbly curve here is what that density function looks like. The dashed one is the theoretical one. But you can see as I move my slice around, I get sort of a different density. What this means that every time I slice through here, I get a distribution. And we can see the PDF of that distribution to the left. And that's exactly what these pictures above here was trying to show. For every point in time, if I go out in the x direction, I can see what the PDF looks like. So here is a slice, for what that PDF looks like. And the same for all these cases. Now, the way you indicate that in Mathematica, so we looked at Poisson process. I can slice by just applying it to t, because it's kind of like applying a function at some point in time. And for some processes, particularly the simpler ones, we can compute that distribution in closed form. So here you can see that there's in fact a Poisson distribution, but the parameter for that Poisson distribution is going to vary by time. Some other simple processes like a Wiener process, you can see that the single slice distribution is just a normal, and you can see how the mean changes, it drifts linearly, and how the standard deviation also changes. Now, we can do the plot that I was hinting at above. We can look at all of these PDFs. So here is time, and here's my state x. And so for each time here, I get some PDF. Okay, so here I'm plotting this infinitely many at the same time. Another way to think about these things as a marginal distribution. If you think of a multivariate distribution, this is computing in marginal, except there are infinitely many of them. So that's a slight complication. Now, the fact that you get a distribution out or a random variable out when you slice means that you have a ways to connect it, and connect it to random variables and distributions, and everything that you expect to work does work. So these are perfectly good random variables. So here's a Poisson distribution. I've sliced it at 1, and now I can use that to simulate, to generate random numbers. I can compute probabilities. So if I slice it at some point t, I can find out what's the probability that the value is less than 5 at that point in time for the process. Now, I kept a lot of things symbolic here, the parameter, the time, and so on. So the answer also includes symbolic parameters. Here's an example of using that. So let's assume that the price of some financial asset is modeled by this process, the Wiener process. And you can make this much more complicated. Now, what I'm interested in so this is a financial option, let's say, and the financial option is worth, I'm betting on the fact that the price is going to be greater than 12, let's say $12. So if the price at some time t, when this option matures, is greater than 12, I get the profit. If it's less than 12, I get nothing. So the way to say that is max of this and 0. So how much profit can I expect? Given that this varies randomly, what's my expected profit? Well, you just formulate it exactly, the way you expect. It's an expectation. And in this case, I kept many things symbolic, so you get something, how it depends on parameters that you add in your process. which allows you to, for instance, see how sensitive it is with respect to many of these parameters. Now, so slice of a process is a distribution. That means that everything we can do for distribution just works. Now, for random processes, many of these things have names. So for instance, if I compute the mean of that distribution, that's called the mean function for random processes. If I compute the median, that's the median function, and a whole slew of other things. The way you call that in Mathematica is just what you see here. Instead of introducing new functions called mean functions and so on, you just apply mean to the sliced process. So here's the mean, median, standard deviation functions, and this is for the Wiener process, and we can see that mean and median grows linearly, and the standard deviation grows like a square root with respect to the... If this was finance, we would call this volatility, but the standard deviation. Okay. We can also compare that from the data side, which we did when we first introduced it here. So let's use a process, let's simulate it, and now I can compute the mean for every point in time for that collection of data. So I have, in this case, I simulate 100 paths from a Wiener process, and I compute the mean by slicing through at every point in time. And this bubbly curve here is what I estimate from data. The dashed one is the theoretical ones. Now, this idea of slices, I can generalize to take more than one slice. So if I put up another bar here, I make a bivariate slice, and I can keep on going. In fact, this is the thing of defining all slice distribution is an equivalent way of defining every process according to the structure theorem by Kolmogorov. So it's not only sort of, cool to do, it's actually the very general definition of a random process. Okay, so we'll see some more practical uses of these. You saw some now, but now we move into the second part of the talk, which sort of dives into some groups of these processes and how you specify them and kinds of things that you might be interested in analyzing. First group is finite Markov processes. And one way to think about them is basically as random walks on a graph. They're finite, so they're a finite number of states. You specify transition probabilities between the states. So here is one way, this is how you can specify a discrete Markov process. You start in the state 3, and then you specify the probability of transitioning from, in the first row, this is the probability of transitioning to state 1 again, to state 2, and then there's zero probability to state 3 and 4, and so on. So this is called the transition probability matrix. If I do that, I can actually, convert that to a graph and look what it looks like. So here I don't put the probabilities, except they are there as tooltips. So we talked about 1, so there's a 0.5%, there's 0.5 probability of going back to 1 again, and there's 0.5 probability to go to state 2. But I can't go to 3 or 4, and we see that by those zeros there. Now, let's simulate this process, a number of times. So I simulated 15 times, and what we can see, if we look at all these, that pretty much either I seem to get stuck in either 1 or 2 and oscillate between them, or I get stuck in 4. If I do it one more time, we should have similar kinds of behavior. Now I get stuck in 4 more often, and we could have figured that out by just looking at the graph, obviously. So there's no way to return to 3. So either I go to either 1 or 2, in which case I can oscillate between them. That's the only thing that can happen. Or I go to 4 and I'm stuck in 4. So that's exactly what we would have guessed from the graph. Now, I can do various analytic kinds of computations too. So if I say that x is from, in this process, now a different way to slice is to sort of indicate the time that I'm slicing in the variable itself. So what's the probability that at time 10 I'm in state 1? That probability is a third. Or over long periods of time, what fraction of time do I expect to be in state 1? If I do many scenarios here. Again, a third. Now, something that we do for many of these classes is that we provide additional service functions that effectively produce a report. And everything that you see here in this table, you can individually call and compute with. But this sort of basic report sort of summarizes a lot of it. So you can see things like initial probability, transition matrix, and some of the structural things that I hinted at. So for instance, one thing that you can see, which are the sort of communicating classes. Communicating classes of states are things where you can go from one to the other. So for instance, if we look over here in the actual graph, we can kind of see that I can go between 1 and 2, but I can never go to anything else. I can't go from these guys to either 3 or 4. When I'm in 4, I can just be stuck in 4, and so on. So that's what those classes are, and they have big impact on when you want to understand the long-term behavior of one of these Markov chains. Often they're big ones that we study. Okay, now another way to define a graph is to just define a Markov process is just to start with a graph, and then we can use, instead of using a matrix there, I just use a graph, and now that's a discrete Markov process, and we can look at it, convert it back to a graph, and we can see that this actually comes from how a knight would move on a chessboard, and I pick a really small chessboard here, just a 4x4. But you can see where they go, and if I hover over them, I can see what the probabilities are. It will pick uniform probability for everything that's reachable out from each node. Okay, let's use that and just simulate it. Here's the simulation. I can sort of run around. You can see this is the state I'm in. This is where I came from. And this is just what I choose because it was kind of confusing to just see the state. And so I'm jumping around like a random, a knight picking random possible moves. If I do that on a slightly bigger chessboard, like a 25 by 25 chessboard, run a simulation, this is basically a random move on a chessboard for a knight. So absolutely any graph, and we already saw, and that graph could be a social network, for instance, It could be, these are my friends, and what's the probability of me getting in touch with such and such through, a rumor getting started somewhere. What's the chance of that, what's the probability of that reaching, so and so. All right, another one, another important class of random processes are queues. Well, we've all been in queues at airports or stores and so on. The mathematical model of a queue is fairly simple. It has an actual queue as we think of a queue. It has a process or a server. In this case, it has one server, but you can also have, for one queue, you can have multiple servers, 3 in this case. In some cases, we can also limit the size, how many we allow to be in a queue. If too many people, if someone tried to enter a queue when it's already full, it will be rejected. So for instance, some real technical systems behave this way. When you lift your phone and try to get a dial tone, if the system is overloaded, it will just reject you. This whole theory was developed in order to be able to understand things like packet switching, which is something that led to Ethernet and subsequently Internet. So all of these are stochastic systems, and the question is, what kind of capacity can you get out of a Ethernet, for instance? It's not clear that it will scale well. But also in modern times, it's used to analyze service, like a call center and things like that. So let's just get a little bit more understanding how this model works. The state of a queue, of a queuing process, is the number of jobs or customers in the system. So here I have a single queue and a single server. The service rate, you give two numbers here, which is the service rate mu and the arrival rate lambda. And this means really that the exponential distribution between the arrivals or exponential distribution between the service finished. Now, if I, so mu is the service rate. If I have more people arriving, so I up the arrival rate, what we see is that we start to get more bubbles, right? We get more, the length of queues goes up, and the closer that I get, the more these bubbles will go up. If I actually pass, so I have more people arriving than can get serviced, they arrive faster than I can service them, I will eventually have a blow up. So here's an example where I blew up beyond my sort of plot range here. So that's something that you might be interested in dimensioning your system to be able to provide decent queue lengths or wait times. Those two are in fact some of the most important things that people are interested in for queues. What's the expected So we again, like we did for Markov processes, we have service functions that give you summary tables. So one of the most important performance measures is system size, which is everybody in the system, whether in the queue or being at the server, or queue length, which is people in the queue. Or what's the expected time to run through the system and get out on the other side. Now, these things, vary, of course, as you generalize. If I have more servers, I get different results. If I have sort of limitations, I get different results. But these are all the things that you kind of would have guessed, probably. Another variant of queues is that we connect them together, like in another network. So, for instance, if you go to an airport, you go to one queue, you go to check-in, you go to security, then you go to boarding, and so on. This happens in technical systems too, like web servers are usually forking off jobs to each other. And so the question is, how does this whole system behave? I won't go into that now, but you'll find examples in the notebook and on our marketing page. Next group of interesting processes are time series processes. Mathematically speaking, a time series process is just a set of difference equations that are driven by white Gaussian noise. You have something that varies with no temporal dependence, that just as input to these difference equations. Practically, you use this as black box models to model things where you don't necessarily have a very good model. So things like unemployment rate or exchange rates or various finance kinds of things. Now, so here is a really simple process. So this is what it means. This is a first order difference equation. And what comes in here is just basically white noise, meaning that it's not dependent on each other in time. Okay, so here's my process. I can compute everything you saw me compute. The mean function is 0. Here's the covariance function. I can compute the slice distribution, which are all, Gaussian here because I drive it with Gaussian. But one important thing that people often are interested in is to look at covariance function or dependence in time. Now, these guys, for processes, they can generally have all kinds of shapes. They're always symmetric. But you see these particular ones for time series, they look exactly the same outside of the diagonal, regardless of where I'm on the diagonal. So around here, it looks the same as around here. That's known as weak stationarity. So people often look at just that particular direction. You look at the covariance function along the anti-diagonal. And so these are pictures that you might recognize. Now, this often you can tell a lot by looking at this about the process. How far in time do things affect each other? So for instance, in this case, I can see that only 2 steps in time can the process affect each other. And if I'm farther out, they're really unaffected. Whereas for this AR process, they affect each other all the way out. Less and less, but they keep on affecting each other. Now, so let's use this to model some data. So I'm going to read in some weather data. Here's the temperature in Champagne. Let's look at it. This is what it looks like. Weather has this particular feature that probably 24 hours later, it's not going to be unrelated to what it was today. So it has sort of this seasonal or cyclic behavior. There's a special class of time series processes that are called, usually has an S in their name for seasonal. So seasonal ARMA process. And I'm going to say that the cycle here is 24. We can also detect that and so on with tests. But let's do this. Let's estimate our process from that. What's going on? I think I've mistakenly defined B. Okay, so there we have estimated the process. Now I can use that process to forecast what the future weather might be like. So let's say I want to forecast it 3 days in advance, so 3 times 24. And now I get, again, a temporal data object. Let's display them together. So here's the measured weather, here's the predicted or forecasted weather. Many more things to say about time series, but let's get on to the final group of random processes. These are stochastic differential equations. They're very similar to time series, except instead of using difference equations, we use differential equations. But again, we drive them with white Gaussian noise. Okay, so let's do a really simple example. So this is basically x prime equals to minus x. But then I want to sort of send in white Gaussian, white noise to perturb it a little bit. So let's simulate that. So I can specify that in a notation, which is very much what you would expect, the classical notation for it. So here's my differential equation, a stochastic differential equation. So let's just look at the first case where I have no noise in. And then we get, as we expect, this sort of deterministic solution, e to the minus t. Now let's then as we add more and more noise in, we can see that gets folded in to the solution. In the beginning, we can't affect it very much, but over time, it sort of compounds itself. And then when I really up the noise level, I get something that's pretty wild. So that's simulation. Now, if I define one of these processes, again, everything works just as I described it. I can compute the mean function, various functions. We can use those two to sort of bound simulations. So here's my simulation. I'm plotting the mean functions plus minus 3 standard deviation, and I expect about 99 or 99% of it to be within these bounds. We can also compute other things like slice distribution. In this case, here's the PDF for the slice distribution, and we can look at it, here with x and t, and we can see that how it sort of follows the mean function, but it gets sort of wider and wider because the noise sort of compounds, and I have less and less localized solution. Many special processes are, in fact, of this kind. So Wiener process we've been using a lot, which is integrated white noise, is one of these. Ito processes, geometric Brownian motion, and many more. These all can be automatically converted into this form to get it there. There's much more to say about stochastic differential equations than all of these processes. But when you want to learn more, so first of all, there's a nice group of marketing pages that's on the What's New site for Mathematica. Here's random processes. You're going to recognize some of the pictures from my talk. And there are similar ones for Markov queuing processes and so on. But also, built into the system, guide page that describes more clearly the scope of the project and so on. And there are separate guide pages for all of the things that we discussed here, and these are also available on the web. That concludes my talk, and I'm sorry, apologize for this. It's a blinding fast presentation, but at least I hope that it gave you some taste of it.
Hey, you certainly covered some great examples there, and there were some examples that we skipped over, but you can download that notebook soon, and you can look at everything that we did not talk about and everything that we did. I do have a quick follow-up question from a viewer. Do you offer priority queues?
We do not. We do offer general queues in the sense that you can have the queues that I showed are called MM1 queues or MM queues, which means that there are exponential times between arrivals, there is exponential time between services finished. You can generalize that to use absolutely any distribution. So those are usually called MG, GM, GG, and so on. We're planning to extend to offer more kinds of queue disciplines. So we also allow for limited queue, but more kinds of queue disciplines include priority queues that you mentioned, but also bulk arrivals. It's another kind that we hope to add in the future.